All right, welcome to our video walkthrough for day 14 from Advent of Code. This is last year's Advent of Code 2021. And day 14, the subject of the problem is Polymer template expansion. What does this mean in programming terms? We start with just a string, series of characters, and each pair of characters in this string essentially expands to incorporate a new character in each step of this problem. So we start out with NNCB, and there are three pairs in that, NN, NC, sorry, can't highlight, and CB. And so each one of those pairs generates a new letter at the second stage of the problem. So the NN pair generates a new C, NC generates a new B, and CB generates a new H. And so some of them are down here. So this section shows the expansion. So we take this and we expand it, inserting all three of those new characters in there. So between the two N's we get NCN, between the N and the C we have NBC, and so on. And we just keep expanding this template for a certain number of steps. For the first part, our goal is to do 10 steps of expansion. So this is, after 10 steps. So apply 10 steps of the pair insertion. And we always want to take the quantity of the most common element and subtract the quantity of the least common element. And for part 2, all we're going to do is 40 steps. And so the key difference between parts 1 and 2, part 1, you can use a more naive approach and just sort of keep one string in memory and just keep doing the modification on that string. With part 2, you need to recognize that the naive approach results in exponential growth. So our string essentially doubles in size each time. So you can do that for 10 steps, so you can't really do it for 40 steps. So you have to do something more clever for part 2. In our code walkthrough, I'll briefly go over sort of the naive algorithm. I just haven't written down already, but we'll essentially use the long algorithm, more clever algorithm for both parts of the problem, since it'll work. But the first thing we need to do with this problem, is with any Advent of Code problems, we need to figure out how we're parsing our input. This input is actually pretty straightforward, especially using a nice parsing library like Parsec. So let's go ahead and just think about how we're going to do this. Okay. This will be our parser for the entire input. So we have this pair map type, and so this is just mapping a pair of characters to the inserted character for each step. And so each line, basically, except for the first line, each line generates a new item for that map. So parse pair code will produce 3 characters. That's one line of our input, and then the whole input will produce a string and the pair map. And so let's actually start with this other part. How do we parse a single one of these lines? Again, this is actually probably one of the easier parsers I've had to write during this time. So we just have, one is a letter character, and then we have another letter character that's just back to back with no space or anything, and then we just use the string, space, and the arrow. And then we get one more letter character that's the output of this pair. And then, so right now we'll just return all 3 characters and say, okay, input 1, input 2, output. And that's all we need to do for that. So to parse the entire input, what do? We have to print the starter template. So I refer to it as starter code. That's just one line where we just say some letter chart. Instead of parsing a single character, we'll parse just a group of them. And then we need to parse 2 end-of-line characters. So we'll do EOL, EOL. Like this, because we have the new line for this line, and then we just have an empty line. That's how the format is. So we'll parse our end-of-line characters, and now we'll get the pair codes. So we'll get, we'll use sep n by 1. It's rapidly become my favorite combinator with Parsec. It just actually works really well for parsing things that are, separated by new lines, like so. And we'll say, so we'll return the starter code, that's our string. Then we also want to go ahead and build our pair map. So we have this function, this takes a list of these character triples and builds our hash map. So we just want to apply that function over our pair codes. And that'll be the result of this, but now we have to go ahead and fill in this function. So this is actually pretty straightforward because it's just a fold. Let's imagine, you know, we'll just fold over our list and say, okay, we have some function, and we'll do it over, we'll start with an empty hash map, and we don't even need to include the list as an argument here because it's going to be an iter reduction. So what are the arguments for our fold function? So we need to take our previous map, and then we take one of these character triples. So we say C1, C2, C3, and ask ourselves, okay, what do we do with this character triple and the map? Very easy. We just say hash map.insert. We make our key, it's the first two characters, and then the value is the last character. We insert that into our previous map. And that's all there is to it. Actually, yeah, like I said, one of the easier sort of intro or parsing steps for any of these problems. So before we get going with the algorithm, let's just do the rest of our little boilerplate code here. So as usual with these problems I've been doing lately, I'm doing almost everything in Monad Logger just for ease of debugging. I found it somewhat useful with this problem, so I'm just sort of sticking with that idea. So we get the pair codes, and we could also say pair map. So we'll use parse file, use this combinator all the time with our parse input. And so I've written basically our function template. We have expand polymer long, or the sort of correct solution to this problem. We take the number of steps we want to run in total, and we'll take our original code, we'll take the pair map, and then we'll return we'll return the integer that's ultimately this difference number that they want. So that's we do expand polymer long, 10 steps for the first part of the problem. Starter code, pair codes. That's all we have to do for the easy part, and it's just hard part the same. Standard outlogging t. All that's different is it's 40. So now let's sort of go over our algorithms and what does the naive algorithm look like? So what's at the root of this is this expansion step. And if we're taking the naive approach, we're just keeping a string in memory that always represents the current state of our algorithm. That just makes things pretty easy. But basically, we just want to run a single step of expansion, and we can do this in a tail recursive way. So we have one string argument that's the accumulation, the accumulation of the new string for the next step. We're gradually building this up over the course of our recursive helper function, and then we have the remainder of the string. We have the stuff we still have to process, and there are basically three different cases. This first case of the empty string being remaining, this shouldn't actually happen, as we'll see when we do the recursive cases. A real base case that should actually happen is that we just have a single character remaining. And all we need to do is we just append that last character to our accumulation, and then we reverse the whole thing and return that. And that's our real base case. But there's not necessarily harm in returning the reverse of the accum in this other base case, but we do want to log that that wasn't supposed to happen. So what does the recursive case look like in this naive approach? So in the recursive case, we have at least two characters at the start of our string, next char and second char. And so we want to start by looking those up in our pair map. Once again, we have this possibility that we look up a pair that doesn't exist. The advent of code input parameters will sort of prevent that from happening. We shouldn't have this happen. So again, we'll log an error if that happens and sort of do something logical, but we don't expect that to happen. So now let's suppose that we get that we insert a character, or that we've found a match for these two characters. So we add two of those to the front of our accumulation string, and so basically what we're doing is we're imagining that we have what's in front and the next one that's beside it. And so what actually gets put on? Remember, we're accumulating in reverse, so we have the accumulator plus the next char, because we're done with the next char, we're not going to use it again. And then we put the insert char after it. And so the second char, we'll put that back into the mix, and so we'll include it with rest because we do want to, each character is part of two different pairs for the most part, except for the first character and the last character. And so we reflect that, and this is where we run our recursion. We have our new accumulation, and we have our new remainder. And so now we have this run step function, which is this is just a wrapper around run expand. It calls run expand with an empty string as the accumulator. This is how tail recursion works, and we include our input because our entire input is still remaining when we start this out. And it has this integer argument. I just did that for the sake of making this an easy fold to write. So we, 1 through num steps, we're just counting the number of steps that we're doing, but really what matters is that we're folding, that we're taking our original input and then turning it into the output. And so we get our final string this way. And then one thing we need to do is we need to build, we need to figure out the number of occurrences of each character in that string. If it ends up being empty, of course, we return nothing. That's an error case. But otherwise, we can take the maximum number in that character map and subtract the minimum number. That is the answer to our problem. Now, this brings me to the utility that I should be referencing already, that we have this idea of an occurrence map, and that just counts the number of occurrences of a single item, and we'll be using that quite a bit in our more complicated solution as well. So again, really this is just a map from some key to an integral value, and we can add a particular number for a particular key like this. So we'll see, we'll use this a couple times. Increment key is something that's very common in adventive code. I've found it's very useful, but it's just a specialization of this add key function where the number we're adding is 1. So we'll use this occurrence map now as we write our more complicated solution. Again, this naive solution is not going to work if, once we get beyond 10 steps, 20 steps, the string it doubles each time in size, and so it'll be too big to fit in memory, and it'll just take way too long. So we can't loop through character by character anymore. What we can do is we can count the number of pairs that are present in our string, and we can just keep track of that number of pairs, and that is actually sufficient to determine what the number of each pair will be in the next step. So it's a little complicated, but let's start working at it. The real key to understand with this problem is the expansion step. So I'm actually going to start there with the run expand step. So occurrence map big, this just means we have integers as the count rather than say word. We want something that is unbounded, because our numbers are actually going to get very big here, as we will see. So what are we storing? So we have these character pairs, and basically we are going to be treating this function actually like a fold as well. So this is going to process a single character pair and count combination from within our map. This will be the most inner part of our loop, and this will return this will be part of our fold, so it's returning the new occurrence map. What actually invokes this? What's our outer loop? Our outer loop is another function that I'll refer to as run step. Again, we're going to have an integer argument that we ignore, so it'll be kind of similar to the run step function from above. So again, we have this count that we'll ignore, and then we'll say, okay, occurrence map big. And so how do we run a full expansion step? And the answer is, so we say m.toList of our previous map, we loop through all of these pairs, and we're going to do a fold over these. So this is what one of those pairs looks like. Has the 2 character key and the integer count. So we're going to say fold m, run expand is our folding function, and we'll start with an empty map. And so that's how we're invoking this expansion. So what does this expand do? It looks at a particular set, at a particular pair of characters. It looks at their counts and determines, okay, what does this tell us about pairs in the next step? And let's work that out. So we start by saying, okay, we have our previous map, we have our pairs, we have code at the character pair. We'll use all of those names in here, and we have the count for that pair. So first of all, let's look it up. In our pair map, incidentally, where we're getting it all the way from up here, we don't need to include it as a separate argument. And so let's suppose we have nothing. Again, kind of an error case. We don't expect that this will happen the way that the advent of code problems are designed. And so we'll go ahead and we'll start by looking this pair up. So we'll say hashmap.lookup code in our pair map. And so if we find nothing, just recalling, we're bringing this pair map from up here. We're just passing that as an input to the algorithm. We don't need, we don't need to carry that down to our folding function as a separate argument. But if we have nothing, again, this is kind of an error case. We don't expect that advent of code will lead us down this path. But we'll say, missing code, leave an error message for that. And we'll just return the previous code update. Now, let's suppose that, in fact, we do find a new character in here. So we'll say if we have a new character, this is the character that's being inserted. So what does this tell us? This tells us we have two new pairs that must appear in our new string. So we'll say let the first of these is our first character with this new char, and the second one, it has the new char first and then C2. So again, we're pulling each of these, and we know that these two pairs will appear in the next string as well. And so then all that's necessary is to take our previous map. So again, this map argument represents the state of our string. We don't need to know the orders of each of the pairs. We just need to know how many of each pair is in that string. And we'll use add key twice. So first of all, we want to say add key, take our previous map, and bump up the first by count, because remember, if we have count of this pair, if that's the number, then each of these new pairs are also going to appear count number of times. So that's this gives us the map after doing one application of this, and now we need to do it again. So we'll say add key this. Now this map is our starting point, and so we'll do the second pair, and again we'll increment it by count. So should be down there. Let me just double check for I missed a couple of equal signs. So that's our syntax issues there. But that's really the core of this algorithm, is running this expansion step. So instead of using a string like we are in the naive approach, we're just using this occurrence map. We're representing our string by just counting the number of pairs. So what do we need to do now? Well, the thing is, we need to turn our initial string into an occurrence map. So let's actually go ahead and make this function buildMapF and have a pair of characters. This will take, so this is, I called this F because I think I was originally using it as a fold, but it's just a normal recursive function. It's not actually, doing anything special. Okay, so our base case, there's no more characters from our input string to add. We just return our previous map. Even if there's just a single character, again, we return the previous map. Those are kind of our base cases. And now let's suppose that, so for our recursive case, so we'll have, our previous map, and then we'll say first char, second char, and rest. So again, we are sure at this point that we have at least two characters remaining in our string, and so that allows us to basically increment the key for that particular character pair. So we're going to make a recursive call. We're going to say buildMapF again, and now we just need our remaining string. So we have our new map and we have our remaining string. So the remaining string, again, we want to use second char again, so we're going to say second char combined with rest. That's going to be sort of this argument for the recursive call. And then we're going to go ahead and make our new maps. We'll say increment key from the previous map. And so we'll use this pair of first char, second char. So that is enough for us to sort of make our starter map. We take our starter code, our starter string, and turn it into a map. Oops. Equals buildMapF. Starting with empty starter code. Now that we've got our starter map, we can use this to actually run the expansion. So we'll get, I think I called a number of different things final, because I kept being convinced that I was pretty much done with the problem at each step of this. But so first we'll get our occurrence map. We'll run the full set of expansions. So we'll say fold M, and we want to do run step. Remember, run step is the wrapper for run expand. And we're going to do run step with our starter map is our initial value, and then we'll just loop through the number of steps, loop through that list. So this gets us the occurrence map that represents our final string. Now, what do we do with this, occurrence map? We actually have to, again, take that from being a map of 2 characters to account to being a map of 1 character to account. Because remember, our answer requires us to know how many characters, not how many pairs of characters. So we have to get what I refer to as the final char count map. And so again, we'll build this with a fold, but I'll sort of write the fold function in a second. Again, we're going to have, this is going to be a different occurrence map, and we're going to take our final occurrence map, which is not at all final, but that's what happens when you write code on the fly sometimes. So we'll write this function count chars. What does this do? This is an occurrence map over just characters. So not character pairs, just characters. And it will loop through a character pair from our final string representation combined with an integer. So that's one element. It's looping through one of these at a time because this is our inner loop function. And it'll return character map again. Oops. Okay. So we take our previous map, we take C1 and C2 and our count. And again, we're actually going to use basically the same pattern we had here, where we do add key twice. So we'll say, okay, first we do add key, previous map, C1 by count. So we increase the value for the first character by that count. And then we have to do this again. We have to say add key again. This map that we just created is our starting map for the second step of this. And we just do C2 and increment that by a count. And now we just have to go back up here and have to use count chars for our folding function here. So we've got our count of characters, except this still isn't the final count because we've been counting pairs. Essentially, it's doubled because each character appears. Each character appears for the most part in 2 different pairs, because all of the items in the middle of the string that aren't on the edges, they're part of 2 different pairs. So we have to divide this by 2, except we have to account for the ends themselves. So I'm actually going to write one last helper function down here. We're going to call this, I call it plot round up. It's like we're doing quotient by 2, except there's some rounding up going on. And it's probably, I could probably write this more efficiently, but whatever. No, what is that? What is that? Autocomplete sometimes is not correct. Oh, wow. Sometimes it is incorrect in exactly the same way twice in a row, and that's a little annoying. But anyways, we have our character, and we have its count. Now, as a general rule, if we have the even case, and we have the odd case. And the odd case is actually easy. Because in the odd case, that means it must be a character on the end, and we know that it's not on both ends, which means that the correct thing to do is to divide by 2 and then add 1. So we're kind of dividing by 2 at rounding up. And so I just say plot by 2 plus 1. Because if we think back to this example here, if the only way there's an odd number is if it's at the end. It could be an even number and still be at the end. However, in that case, it's still, that's right. I'm not thinking of this right because we're looking at this representation instead of thinking about the pair representation. Let's just think of a pair representation of our very initial string. We have a pair NN, NC, and CB. The ends are actually going to be counted 3 times because this end is part of 1 pair and this end is part of 2 pairs. And so the only way that can happen is because this n is on the far left, and so the correct thing to do is to divide by 2, take the quotient, which gives us 1. 3 divided by 2 is 1 in integer addition, but we have to add another 1. Now there is an edge case There is an edge case where if the same character is on both ends, then we have to do something special. And so we say, okay, if it's even, say quad I2, that's our base. But if the head of the starter code is C and the last of the starter code is C, then we have to add another one. Otherwise, we add 0. Whoa, equals, wait, where'd you get cadmium? Again, autocomplete is being a problem. So if, and luckily we can compare to the starter code because the first and last characters of our string never change. We're always expanding in the middle, and so we can just look at the starter code. We don't have to track everything throughout. So we've got this function, and so that will take our final thing, final counts equals map plot roundup. And now we'll just kind of do the same thing we did before. If null final counts, we'll log an error. Again, that's kind of a problem. Don't expect it'll happen. We'll return nothing. And then finally, our just case, or not our just case, but our not null case will return, say just from integral maximum of final counts minus minimum of final counts. And that will just get everything there for us. Now, I think this is pretty much the complete solution, so we can go ahead and just start trying to compile it, see if I made any mistakes or missed anything. What did we? Okay, 97. We made a mistake here. Build pair map. Oh no, the mistake's actually probably here. I just missed an equal sign. That's always annoying. Okay, now it compiles. And so our most basic case we can do is if we say okay, day 14, easy small. Did I? Okay, 1588. That's I believe that's that's what we should get here. And so let's just go ahead and run the tests. And I did write a few for this day specifically, and we should see that all of those pass. So a bunch of output, and okay, all of our day 14 tests pass, which means we are done. So that's all for the day 14 problem. Next week, I'll do the same thing I did with day 14, so I'll just do it with a new problem. So stay tuned for that. Come, check it out. Written write-up on the blog on Monday, and then I'll have a video walkthrough like this one on Thursday. So thank you so much for watching, and make sure to subscribe. If you are liking this content, subscribe to the Monday Morning Haskell monthly newsletter. Link for that is in the video description.